All right, everybody, this video lesson is going to cover something called photoelectron spectroscopy, sometimes referred to as photoemission spectroscopy, or just simply PES. First of all, what is it? Well, basically, it refers to the energy that is added to an atom, and once that energy is added, the electrons are emitted. Basically, the concept is that electromagnetic radiation gets shined onto a solid, liquid, or gas, and what happens is they determine how much energy it takes to remove electrons from a particular energy level or orbital. This picture shows an X-ray coming in and interacting with some electrons. The incident X-ray comes in, and if the energy is high enough, it knocks out all the electrons on that particular energy level and orbital. This particular one shows the amount of energy that is able to penetrate all the way down to the 1s and eject an electron off of the 1s orbital. That energy needed to emit an electron or eject an electron from an atom can be measured and then graphed into what is called a photoemission spectrum. If I were to summarize it up into a nice little neat box and tie a bow on the top, it's basically what I like to think of as a 2D graph of ionization energies for different elements. And the information you can get off of these photoemission spectrums is ionization energy and also information about the electrons in the electron configuration. The three things that are most applicable to photoemission spectroscopy are electron configurations, ionization energy, and atomic radius. These are the three things that you can deduce when looking at a photoemission spectrum. Here is a PES spectrum of hydrogen. And what you can see, first of all, is that the vertical axis represents the relative number of electrons. So the higher the peak on the PES spectrum, the more electrons there are at that particular energy. This horizontal part of this graph represents the energy that is needed to dislodge those electrons in those particular energy levels and orbitals. And so as you can see, in hydrogen's case, it takes 1.31 megajoules of energy to dislodge one electron. We all know that hydrogen has one electron in the 1s orbital, and so this peak could basically represent the electron configuration for hydrogen. It'll make more sense when you see it compared to helium. Here's helium's spectrum from a PES spectrum. As you can see, the peak has shifted down towards the left because the atom gains an electron and gains a proton, and the atom is overall smaller. Remember, the trend of atomic radius is that elements decrease in its radius as they move to the right on the periodic table because of the increased effective nuclear charge. More protons pulling on more electrons means tighter atom. Now, a tighter atom means that it requires more energy, and as you can see, it was at 1.31, but helium now has energy 2.37, or almost double the amount of energy needed to dislodge its electrons. Furthermore, the intensity of the peak, or the relative number of electrons, has doubled as well. Remember, hydrogen's peak only went up like right here, so it's only one electron. This then, you could say, would be the electrons in the 1s orbital. There are two of them, and they are closer to the nucleus or more tightly bound. Now we jump to a gigantic atom, scandium, for example. Scandium has an atomic number of 21. And we can confirm that if we count the number of electrons that are represented in this PES spectrum. Notice how these peaks are kind of grouped together locally, which means that this first group probably represents the electrons in the first energy level, s orbital. Well, I'll just label that first energy level. This second group of peaks represents the second energy level, and this third group of peaks represents the third energy level, and this fourth group of peaks maybe represents the fourth energy level. Furthermore, you could see that the peaks in a particular energy level are split up. You've got one smaller peak followed by a much larger peak. It would be safe to assume that this first peak here represents the s orbital, and this peak represents the p orbital of this energy level in scandium. And the higher the energy that it takes to dislodge these electrons, you'd suspect they're closer to the nucleus. They're tighter in because it takes more energy to dislodge those electrons. Take a look at the third energy level here. These are the s electrons of the third energy level, and these are the p electrons of the third energy level. And notice that it takes less energy here to dislodge the third energy electrons than it does to dislodge the second energy electrons because they're further from the nucleus. And the further they are from the nucleus, the easier they are to remove, which requires less energy to do so. Remember, this energy here is the energy input to remove electrons. Another key thing to notice is that this P peak, which I've labeled P, is 3 times larger than the S. Well, we all know that you can fit 2 electrons in an S orbital, and since this is 3 times as large, 3 times 2 is 6, and it happens to be the case in a p orbital that there are 6 electrons in the p orbital. What I find interesting about PES is that it confirms the existence of the quantum mechanical model. We developed the quantum mechanical model, or I guess Schrödinger and Heisenberg developed the quantum mechanical model back in the 1900s and the 1910s, but the PES spectrum helps illustrate how these electrons group together first and foremost by energy levels in different regions around the nucleus, and as they get further away, they get easier and easier to dislodge. And the second thing is that they split those electrons into 2 different regions, which we call orbitals, within an energy level. So if we start counting electrons, S2 and S2, that's 4 and 6 makes 10, 12, 18, and then we've got 2 electrons here and 1 electron here. Now what's interesting here in this 4th energy level region is, remember, there's some overlap between the 3D and the 4s energy level. This is the 4s, and the 3D, as you can see, is slightly closer to the nucleus. Even though it fills second, the 4s fills before the 3D. When it comes to dislodging the electrons, it takes less energy to remove the 4s electrons than it does to remove the 1 3D electron. Remember, when discussing the concept of ionization energy, adding electrons to the 3rd and 4th energy level, the 3D fills after the 4s, but when it comes to start removing electrons from scandium in this case, the 4s go first, which is confirmed by the fact that these are lower energy or easier to dislodge in a PES spectrum. And if you count up all the electrons, you get 21 electrons. One of the applications of a PES spectrum is to be able to identify an element based on the total number of electrons, assuming you know that the element is indeed neutral. Now, the following PES spectrum that I'm going to show you come from the University of Arizona website. And notice the scale is now reversed. Before, the scale was bigger on the left and lower on the right. Now they're going to be more normally lower on the left and increase as you go to the right. But that just means that the further to the right and further up the electrons are, the closer they are to the nucleus. So once again, here's hydrogen. And hydrogen's peak represents 1 electron, and it exists at 1.31 energy units. Now, they don't label the energy units, but before we called it megajoules. But it doesn't really matter what the energy is. It could be joules, could be electron volts, but we just know that the energy increases as the electrons get closer to the nucleus. This next one is once again for helium. And notice down here on the bottom in the blue box, you'll be able to identify the element based on what the name is down here. Notice the peak shifts further to the right and doubled in size because there's now 2 electrons in an orbital that's still the 1s orbital, but it's closer to the nucleus due to increased effective nuclear charge. Now, here's lithium. Now, its first 2 electrons go into the 1s orbital, and those get more and more difficult to remove as the element gets smaller and smaller. Furthermore, you're adding more electrons on shells and energy levels over that, and so you get more shielding of the core from the valence electrons. In this case, the valence electrons shield the core electrons from being removed rather than the other way around. The core electrons can shield the valence electrons from feeling the effective nuclear charge. But these electrons right here represent the 2 and the 1s, and that means that this right here is the 1 electron in the 2s orbital. Now, as we build these atoms with more and more electrons, you'll continue to see this electron peak shift higher and higher energy because you're getting repulsion from the electrons in the valence shell, and the element is adding more protons to the nucleus, which pull these 2 electrons in tighter and tighter and tighter, increasing the effective nuclear charge from the nucleus to the 1s electrons. And you'll see this continue to shift higher and higher due to increased nuclear charge from increased number of protons in the nucleus. In fact, this has pulled the electrons from the 1s orbital in so tightly that it needs a new line. So this up here still remains the 1s electrons, but they are now greater than 10, so they get placed down on the line above, the line that goes from 10 to 100. This first line remains 0 to 10. Now these 2 electrons represent the 2 electrons in the 1s orbital. And they themselves have shifted a little bit down to the right because of an increased effective nuclear charge. We now have 4 protons pulling on 4 electrons. And as we know, the atomic radius decreases moving to the right, which is evidence because these numbers both become more and more energetic, or higher energy, or more energy to dislodge. Now let's do some comparisons of some PES plots between 2 different elements. Typically, we look at 2 elements that are stacked on top of each other in the periodic table, or 2 elements that are next to each other on the periodic table. Here are hydrogen and lithium. What you can see right away is that hydrogen, which is a 1s1, and lithium, which is 1s2, 2s1, the 1 electron in the valence shell is indeed represented by this peak that's lowest in energy. But notice that lithium's number is much smaller than hydrogen's number because it's on the 2nd energy level. In fact, it's a level away from the nucleus, and there's some shielding going on from the 1st energy level to the 2nd energy level electron in lithium. And so its number gets smaller. Hydrogen has no shielding, so this electron, this 1 electron, is indeed a valence electron, but it's also a core electron and is held on a little bit tighter. Here's a look at potassium and sodium. First of all, take a look at the magnitude of the energy for these 1s electrons. For sodium, it's only about 104 energy units, call it kilojoules, but this one is 347. Well, potassium's 1s orbital is contending with 19 protons pulling on these 2 electrons, and so that energy is very high compared to only 11 protons pulling on these 2 electrons. You can make the same distinction between the 2s electrons of potassium, which are being held with 37.1 kilojoules of energy needed to dislodge, but the 2s electrons down here are only 6.84, again, due to the fact that potassium has 8 more protons pulling on those electrons. And the trend maintains even in the p electrons. Look at this, sodium's 2 p electrons are sitting at about 3.67 kilojoules of energy, where potassium's are at 29.1. Both of them are 2p electrons, but these clearly are bound much tighter and are closer to the nucleus. And finally, if we isolate or focus in on just the 1 valence electron of each sodium and potassium, sodium's valence electron is in the 3s orbital, where potassium's in the 4s. And you can see the 4s orbital has lower energy than the 3s orbital. It's easier to dislodge this due to the fact that there is 3 energy levels of shielding happening here, where there's only 2 energy levels of shielding happening in sodium's case. You can also compare 2 elements that are located next to each other on the periodic table. You're looking at nitrogen with 7 electrons and oxygen with 8. And I've gone ahead and labeled the different peaks based on what their energy levels and orbitals are for those particular peaks. First of all, as we established, oxygen's electrons in the 1s orbital are held more tightly due to a stronger effective nuclear charge. 1 more proton over here in oxygen than nitrogen means those 2 electrons are experiencing a stronger effective nuclear charge. Now the 2s electrons, which are this peak over here and this peak over here, they're showing less of a drastic change in the energy, 2.45 for nitrogen, but 3.04. But it is slightly higher for oxygen, again, due to the increased number of protons. But what I do want to point out is that the 4 electrons in the oxygen's 2p are slightly less energy, 0.09 kilojoules less than the 3 electrons of nitrogen's 2p. And remember, a half-filled orbital is in fact more stable than a over half-filled orbital. And if you think about the electron boxes of nitrogen, there is 1 electron in each of the 2p boxes. So for nitrogen, in this case, it has a nice even fill of the 2p orbital, which is located by this peak right here. But oxygen actually has a 4th electron, which means that 1 of the orbital boxes is doubled up. And a more than half-filled orbital is slightly less stable. And that means that that 1 electron is going to be a little bit easier to remove. And that indeed is reflected in this slightly diminished, even though there are more electrons here, it's slightly less energy or easier to dislodge their 4 electrons because it's a little bit less stable than having 3 in an evenly filled orbital. Now I'd like to point out that this slight trend actually falls apart as you move further and further down the table. Like for example, up here on this periodic table, if you compare phosphorus and sulfur, you're not going to notice this very much. The half-filled phosphorus, which compared to the over half-filled sulfur, are not going to show this sort of trend. It's not a trend that repeats itself further on down the periodic table. But it is one that represents or shows itself more strongly in the d orbital, with a half-filled d orbital compared to a slightly over half-filled d orbital, like comparing a d5 to a d6, for example. So in the end, you might be asking yourself, how am I going to be assessed on these problems? And here's an example multiple choice problem that I've inserted into this presentation. Notice that these two spectra specifically talk about the removal of a 1s electron from either nitrogen or from oxygen. And if you read through the question, it asks which of the following statements accounts for the peak of the nitrogen being further to the right, or in other words, slightly less energy than the peak for oxygen. In the answer choices provided, the option for letter D is the one that makes the most sense. Oxygen has one more electron than nitrogen does, and both of them have electrons in the 1s orbital that are being pulled by the nucleus. And if you have more protons in the nucleus, like oxygen does, you'd expect the s electrons to be bound more tightly and require more energy to be dislodged. Now I'm going to talk a bit about A, B, and C and why they're incorrect. First of all, A talks about a p subshell. Well, we don't care about p subshells, and p subshells have little to no effect on the 1s electrons being discussed in this problem, and so this doesn't make any sense. Likewise, C talks about p subshell electrons of oxygen. Again, I just stopped reading because p has little effect on the 1s orbital. And finally, B talks about there being electron repulsion, and more so in oxygen than in nitrogen. Well, actually, in the 1s orbital, they both have 2 electrons, so their repulsions should be the same. Which leads me by a process of elimination to letter D being the correct answer. A, B, and C are incorrect, but D is definitely the most correct. Here's another application of PES spectrum, and basically just what element is being represented by the spectrum. And basically what you can do is count up the electrons. Now, what's important to note is that each line represents a half of electron in this particular graph, because we know that one peak equal to another peak might only represent the 1s and the 2s electrons. And we know that you can't have 4 electrons in an s orbital. You max out at 2, which means that each one of these lines really represents a half electron. So if that's 2, then that's 2, then this must be 2 between here, which means that this is 1 electron. So 2 plus 2 plus 2 plus 1 gives me 7, or the correct answer, which is nitrogen. Now this question asks you to compare lithium and beryllium based on their 2s electrons. And which statement below best describes the difference in intensity and positioning of the peak, which is represented by the 2s electrons? Now, we know because lithium and beryllium are both in the second period of the periodic table that their second energy level is their valence shell. And the fact that lithium has 1 electron in the valence shell versus beryllium having 2 electrons in the valence shell should be a big deal. And after reading over the options, you should come to the conclusion that letter A is the correct answer. Beryllium has a greater nuclear charge than lithium and has more electrons in the 2s orbital. And as a result, the 2s peak should shift further to the left or higher in energy compared to lithium, which only has 1 electron in the 2s orbital and only 3 protons in the nucleus compared to beryllium with 4. Now looking at all the other options, we can determine why they're incorrect. First of all, letter B talks about beryllium having a greater repulsive force due to more electrons in that second energy level, or that second orbital. But repulsive forces would actually weaken the electron's ability to stay close to the nucleus. And because there's weaker forces, you'd expect this peak then to be lower than that of lithium. Repulsive forces actually help explain why electrons are not held as tightly, but this peak shows me that the electrons are held more tightly than lithium. So it must not be the repulsion that is playing a role in the fact that the peak is shifted further to left or higher energy. Option C is not correct because lithium does not have a greater pull from the nucleus. In fact, beryllium has a greater pull from the nucleus on the 2s electrons, so we can toss out letter C. And letter D can be thrown out because it mentions lithium having a greater electron shielding. But in fact, they both have equal electron shielding of the 1s orbital because they both have 2 electrons in the 1s orbital, so electron shielding should not play a role. This next practice problem talks about the difference between phosphorus and sulfur. And as you can see, it's specifically talking about why the 2p peak for sulfur seems to be further left than the 2p peak for phosphorus, which you can see in comparison here. Sulfur is further left than phosphorus. But the 3p peak for sulfur is actually slightly further to the right than the 3p peak for phosphorus. I labeled the peaks for easier comparison. Now, after reading through all the options, once again, letter A is the correct answer here. Now let's talk about why B, C, and D are not correct. Now, option B talks about a greater effective nuclear charge, and that's true. S does have a greater effective nuclear charge because it's got one more proton pulling on one more electron. But it talks about shielding, and the fact that shielding is equal in both of these because they have the same number of core electrons. And so you can't say that this shift in peak is due to the shielding because shielding is equal. Option C talks about S having a greater number of electrons than P. And once again, I agree with the first half of that statement. But if something has more electrons than something else and they're in the same row of the periodic table, then it has a stronger effective nuclear charge. And it would be closer to the nucleus, not further away. And if something's closer to the nucleus, you'd expect it to be higher energy. But as you can see, it's slightly less energy than its counterpart phosphorus. Option C once again talks about the S having a greater number of electrons than P. And once again, I agree with that. But the Coulombic attraction, or in other words, the positive-negative attraction between the electrons and the protons, should make the sulfur a little bit stronger or smaller. And once again, you'd expect that mean to have the sulfur 3p peak to be slightly higher energy, but again, it's slightly lower. So greater Coulombic attractions should result in higher energy, but the data doesn't support that, so D cannot be correct, leaving us with only A as the logical conclusion. Finally, we'll leave you with this particular question. Looking at the spectrum of Na and K, which of the following would best explain the difference of the binding energy of the 3s electrons? First of all, the difference between the 3s electrons in sodium and potassium is that sodium's 3s electron is a valence electron, and the potassium is a core electron. Looking at the answer choices, the answer is A. Now let's talk about the three options and why they're incorrect. First of all, option B talks about how K has more electron-electron repulsion than Na. And in order to have more than something, then the other must have some in comparison. And the fact is this, that sodium's one electron is a valence electron, and so it doesn't have any electrons over the top of it. No electrons over the top means no electron repulsion to force it down towards the middle. So the word more would insinuate that sodium has some, and in fact, in the 3s orbital, sodium has no electron repulsion, and so, logically speaking, you cannot choose B as a correct answer. Now, option C, Na has one valence electron. Well, I would say that potassium also has one valence electron. It's not in the 3s energy level, but it also has one valence electron. So simply having one valence electron does not describe the situation that you observe in the 3s orbital between sodium and potassium. Potassium also has one valence electron, but that doesn't explain the increased energy of the 3s orbital. And finally, Na has less electron shielding than K. In fact, because they're both having electrons in the third energy level, they have equal shielding. They both have the same number of electrons underneath them. They both have a full 2s, a full 2p, and a full 1s. And so they each have the same amount of electron shielding. So that cannot be the reason why K is higher energy than Na. So the answer is A. K has a greater effective nuclear charge. It's got all those protons, 19 of them, pulling on the 3s electrons compared to sodium, which only has 11 electrons pulling on the one 3s electron. Well, that takes care of this video lesson on PES. Thanks for listening.